In Chapter 19, we discuss simulation. Simulation is used to estimate the probability of complicated events using a basic probability model and a table of random digits. These are the concepts that we will discuss in Chapter 19. Where do probabilities come from? Simulation basics, thinking about independence, and more elaborate simulations. Probability models allow us to calculate the probabilities of complicated events, starting from an assignment of probabilities to simple events. Unfortunately, the math needed to do probability calculations is often difficult. However, once we have a probability model, we can use a computer to simulate many repetitions. So let's give the definition of simulation. Using random digits from a table or from computer software to imitate chance behavior is called simulation. Simulation is an effective tool for finding probabilities of complex events once we have a trustworthy probability model. We can use random digits to simulate many repetitions quickly. The proportion of repetitions in which an event occurs will eventually be close to its probability, so simulation can give good estimates of probabilities. To effectively estimate a probability using simulation, we'll go through the following steps. Step 1. Give a probability model. Step 2. Assign digits to represent outcomes. And Step 3. Simulate many repetitions using a table of random digits. Let's do an example. If we toss a coin 10 times, what is the probability there will be a run of at least 3 consecutive heads or 3 consecutive tails? First, we must give a probability model for this experiment. Fortunately, because it is essentially the same experiment performed 10 consecutive times, the model is fairly straightforward. Our model in this case has 2 parts. First, each toss has a probability of 0.5 of being heads and 0.5 of being tails. Second, each toss is independent of the previous toss. In other words, the outcome of the next toss does not depend on the outcome of the previous toss. Next, we must assign random digits to outcomes. Recall in a table of random digits, each of the digits 0 through 9 has a 0.1 chance of appearing, and successive digits are independent. Now there is more than one way to do this, but we must assign half the digits to represent heads and the remaining half to represent tails, as each outcome occurs with probability 0.5. In this example, we'll let odd digits represent heads and even digits represent tails. Third, we carry out the simulation. Each string of 10 random digits represents 10 tosses of a coin. Recall, we're letting odd digits represent heads and even digits represent tails. For instance, let's look at 3 repetitions. Here we looked at 30 consecutive numbers in a table of random digits. The strings of 10 will represent our 10 tosses. We will look in a string for 3 consecutive even or 3 consecutive odd numbers, as this represents a string of either 3 straight heads or 3 straight tails. For instance, in repetition 1, there was a run of 3 heads, as the numbers 3, 9, and 5 all appeared in a row. In repetition 2, there were 3 runs of 3 heads or 3 tails. And similarly, there is a run of 3 in repetition 3. Now suppose we repeated this process 25 times, and in 23 of them, there was a run of 3 or more heads or tails. Then we would estimate the probability of such an event of occurring at 23 over 25, or 0.92. Before discussing more elaborate simulations, it is worthwhile to discuss the concept of independence. Two random phenomena are independent if knowing the outcome of one does not change the probabilities for outcomes of the other. The simplest example of independent events are consecutive tosses of a fair coin. The tosses are independent as the outcome of the first toss does not change the probability of heads or tails on the second toss. To show two events are independent, there are a few approaches that we can take. One method is to use the definition of independence. This is best saved for a formal probability course. Another is to use the correlation. Although this can't prove that two events are independent, it can give us a sense to it. This approach applies to numerical variables in a sequence of n trials. If the two variables are independent, then there should be no straight line relationship between them, and thus they should have a correlation close to 0. Let's look at another example. A couple plan to have children until they have a girl or until they have 3 children, whichever comes first. What is the probability that they have a girl among their children? First, we need our probability model. It is almost identical to our coin tossing model. However, having a girl is slightly less likely than a boy when a child is born. In addition, we will still assume that the sexes of successive children are independent. In other words, the sex of the first child does not change the probability of the sex for the second child, and so on. Next, we assign digits to outcomes. Because the probabilities are not exactly 50-50 like with coin tossing, we'll need to assign outcomes to 100 digits instead of 10. The probability of a girl is 0.49, so the first 49 digits will be assigned to girl. The probability of a boy is 0.51, so the remaining 51 digits will represent boy. Now we carry out the simulation. We will read pairs from a table of random digits until the couple have a girl or 3 children. Below are 10 repetitions using line 130 of table A. In all but one of the 10 repetitions, the couple had a girl. For instance, the first repetition is 6905. The repetition stopped at 05 as the couple's second child was a girl. So, based on the results of our simulation, we would estimate that the probability that the couple will have a girl with this strategy is 9 out of 10, or 0.9. If our probability model is correct, the true probability of having a girl is 0.867. Our simulated answer came quite close.